Life cycle and evolution of massive stars. In recent years, the star has exhibited dramatic fluctuations in brightness, with mysterious dimming and brightening episodes sparking intense speculation among scientists and enthusiasts. These variations are believed to signal the star's impending demise, suggesting that Betelgeuse may soon explode in a spectacular supernova. A supernova marks the violent death of a massive star, but it also plays a vital role in the ongoing creation of new stars, planets, and the elements necessary for life itself. When Betelgeuse finally goes supernova, the explosion will be an unprecedented celestial event, likely visible in broad daylight and capable of outshining the moon for weeks or even months. At its core, Betelgeuse has been undergoing nuclear fusion, a process that converts hydrogen into helium and releases tremendous energy. As the star aged, it depleted its hydrogen reserves and began fusing heavier elements like carbon and oxygen. Eventually, it reached iron, a dead end for stellar fusion. Unlike lighter elements, fusing iron does not produce energy, and this lack of outward pressure allows gravity to take over, causing the core to collapse in on itself. This sudden implosion triggers a cataclysmic explosion, a Type II supernova, releasing a burst of energy and ejecting vast amounts of stellar material into space. Astronomers are vigilantly observing B2 with ground-based telescopes and space observatories, while facilities designed to detect elusive particles such as neutrinos and gravitational waves are on high alert. Neutrinos, nearly massless subatomic particles that can pass through matter virtually unhindered, often escape the core moments before the light from a supernova becomes visible. Advanced detectors like Japan's Super Kamiokande and the IceCube Neutrino Observatory in Antarctica are poised to capture these fleeting signals, offering a rare glimpse into the final moments of the star's life. The eventual explosion of Betelgeuse will unleash a titanic amount of energy. In just a few minutes, more than our Sun will emit over its entire 10 billion-year lifetime. This energy will radiate across the electromagnetic spectrum in the form of visible light, gamma rays, and other high-energy particles. The blast will also hurl heavy elements such as iron, gold, and uranium into the surrounding interstellar medium. These elements, forged in the heart of the dying star, are essential for the formation of new celestial bodies, and even for life as we know it. Thus, the death of Betelgeuse will contribute to the cosmic cycle of destruction and renewal, seeding the galaxy with the building blocks of future stars, planets, and possibly civilizations. The supernova will also generate an intense wave of electromagnetic radiation, allowing astronomers to study the event across multiple wavelengths using observatories like the Hubble Space Telescope and the James Webb Space Telescope. These instruments will provide critical data that will refine our understanding of supernova dynamics, including the mechanisms that lead to the creation of neutron stars or black holes at the heart of such explosions. Because of Betelgeuse's relatively close proximity to Earth, its supernova will be unlike any previously observed stellar death. While most supernovae occur in distant galaxies and are often obscured by interstellar dust or are too faint for detailed study, Betelgeuse's eruption will be observable in exquisite detail. This proximity offers a once-in-a-lifetime opportunity to examine the physics of core collapse and stellar evolution with unprecedented clarity. Scientists will be able to observe not just the light and radiation from the explosion, but also the gravitational waves generated as the core collapses, ripples in the fabric of spacetime predicted by Einstein and first detected in recent years. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo are prepared to detect these waves, which will reveal new information about the violent internal processes that govern stellar death. The disappearance of such a luminous and familiar star from the night sky will not only be a scientific milestone but a cultural one as well. For millennia, humans have looked up at Orion and found inspiration in the glow of Betelgeuse. Its sudden absence will serve as a poignant reminder of the universe's impermanence and the transient nature of even the brightest lights in the sky. The event is expected to reignite public interest in astronomy, drawing attention to the larger mysteries of the cosmos and our place within it. Despite the enormous energy released, Betelgeuse supernova poses no threat to life on Earth. Its great distance ensures that the radiation and cosmic rays will dissipate across the vastness of space before they could impact our planet. At most, the event may slightly disturb Earth's upper atmosphere, possibly enhancing auroral activity. The vibrant light displays typically confined to the polar regions could temporarily appear at lower latitudes, offering a rare and beautiful spectacle for skywatchers around the world. The scientific value of observing a nearby supernova cannot be overstated. These explosions are responsible for distributing the heavy elements that form the very matter of planets and people. They also offer crucial insights into the nature of dark matter and dark energy, the mysterious forces that govern the universe's structure and accelerate its expansion. By analyzing the data from Betelgeuse's explosion, Researchers hope to answer foundational questions about how matter behaves under extreme conditions, how black holes and neutron stars are formed, and how the universe recycles its contents to create new systems. Betelgeuse's final act will serve as a powerful illustration of the interconnectedness of cosmic events. The matter expelled during the explosion will one day coalesce into new stars, planets, and potentially life, continuing the eternal cycle of cosmic evolution. This dynamic process underscores the idea that in the universe, destruction and creation are not opposites but rather two sides of the same celestial coin. The tools available to today's astronomers are more advanced than at any point in human history, making this imminent supernova an unparalleled research opportunity. From powerful space telescopes to supercomputers capable of simulating core collapse physics, modern astrophysics is equipped to capture and analyze the event in extraordinary detail. These capabilities will enable scientists to refine theoretical models of stellar explosions, which until now have largely been based on incomplete data from more distant supernovae. Betelgeuse offers a near-perfect natural laboratory to test hypotheses about the thresholds and conditions that lead to the formation of black holes versus neutron stars. Researchers will pay particular attention to the behavior of the star's collapsing core, using observational data to calibrate and improve models that describe the most extreme environments in the universe. The supernova will also produce a burst of gravitational waves, a phenomenon that until recently was purely theoretical. These waves, subtle distortions in spacetime itself, carry crucial information about the internal structure of the collapsing star. By examining the waveforms captured by instruments like LIGO and Virgo, scientists can probe the interactions of matter, energy, and gravity in ways never before possible. This could lead to transformative insights into high-energy astrophysics and the fundamental laws of nature. Betelgeuse's proximity enhances the value of these observations, making it possible to collect data that is both rich in detail and temporally aligned across multiple detection platforms. This synchronization of neutrino, gravitational wave, and electromagnetic observations will set a new standard for multi-messenger astronomy. As we await the explosive finale of Betelgeuse, the global scientific community and the general public are united in a sense of anticipation and awe. The star's supernova will be more than just an astronomical event. It will be a historic moment that marks the culmination of decades of observation, speculation, and technological advancement. When the light from the explosion finally reaches Earth, it will not only illuminate the night sky but also shed light on the enduring human quest for knowledge and our profound connection to the cosmos. Betelgeuse's death will be a beacon of curiosity, a cosmic signal that inspires new generations to look upward and question the nature of the universe. It will highlight how far we've come in our ability to understand the stars and how much more there is yet to discover. As it explodes, Betelgeuse will remind us that every ending in the universe is also a beginning, that in the ashes of a dying star lies the foundation for everything that is yet to be born. Betelgeuse's imminent supernova stands as a singular moment in human history, one that unites the scientific community, space enthusiasts, and even casual skywatchers in awe and curiosity. The expected explosion, while rooted in complex physics, transcends equations and data, becoming a profound cosmic story unfolding in real time. The life of a star is measured not in years but in epochs, and Betelgeuse has spent millions of years evolving from a main sequence star into the red supergiant we see today, swollen with age, nearing its final breath. The final stages of such a star's life are marked by increasing instability. Once the fusion of iron in the core becomes unsustainable, gravity overwhelms the internal pressure that had held the star up for eons. In the blink of a cosmic eye, the core collapses and rebounds, triggering a titanic release of energy in the form of a Type II supernova. Unlike anything else in the natural universe, a supernova compresses the violence of billions of atomic bombs into a singular cataclysm, releasing neutrinos, light, and shockwaves that ripple through space for millennia. This process doesn't merely signify death, it sows the seeds of new creation. Elements forged in the heart of Betelgeuse, from oxygen and silicon to gold and uranium, will be scattered across the cosmos. These are the very elements that make up planets, oceans, mountains, and even the blood in our veins. In a way, the death of one star becomes the birth cry of countless future worlds. For astronomers, this is not just poetic, it's empirical. Observing a nearby supernova like Betelgeuse gives scientists a front-row seat to the alchemy of the universe, a live demonstration of how matter is redistributed and recycled across galactic scales. The physics of core collapse supernovae are not yet completely understood, but this rare celestial event will yield insights that decades of distant observation have only hinted at. Every wave of radiation, every pulse of gravity, every neutrino captured by detectors across the globe will help decode the secrets of stellar death. Thanks to modern observatories like LIGO, Virgo, IceCube, Hubble, and the James Webb Space Telescope, we now possess a toolkit capable of capturing nearly every facet of a supernova's eruption. Gravitational wave observatories will listen for the trembling of space-time itself as Betelgeuse core collapses. Neutrino detectors buried deep in the Earth will record ghostly particles that escape the dying star before light ever does. Space-based telescopes will span the electromagnetic spectrum, imaging the explosion in infrared, ultraviolet, X-ray, and gamma-ray wavelengths. This multidimensional approach to cosmic observation is a marvel of modern science, and it ensures that Betelgeuse's final performance will not be missed or misunderstood. What makes this event even more impactful is its visibility to the naked eye. For countless nights throughout human history, Betelgeuse has blazed in the shoulder of Orion, one of the most iconic constellations in the sky. Its red-orange glow has guided sailors, inspired poets, and challenged astronomers for generations. The day it vanishes in a brilliant flash, humanity will collectively look up, not in fear, but in wonder. The explosion could light up the daytime sky, casting a second sun for days or even